All right, we're back on. Thank you. Okay, homework 0 is due today. And the midterm exam, I think I announced this, but let me announce it again. So here's the midterm. So it'll be on Thursday, October 9th, which is 2 weeks from today. And it'll be open book, open notes, and its main purpose is feedback for you, because the last day to drop a course without receiving an F is Friday the 17th. So that means that if you take the exam on Thursday the 9th, I can get it back the following Tuesday, discuss it in class, and then you'll have some feedback information. Okay, any questions about anything? I still have some homeworks to get back to Ambreen and Stefanoff. All right, are there any questions? What was that?
This is homework.
This is homework 0.
Yeah. Conversion. But that's the first one.
You want to know how to do it?
Yeah.
Okay, well, I'll grade them and give them back, and then I'll give the solution. Okay, thank you. Okay, so the last thing we were talking about was independence, section 3.5, and I had started that briefly.
Sir,
Question?
Let me ask you one question.
What was that?
How do you allocate the final grades for the course? In terms of final midterm?
The grading policy is based primarily on the final exam, but the homeworks are factored in the following way. Actually, 2 ways. There's going to be a lot more homework, so after the exam, the homeworks will come at a regular rate, because so far, you haven't learned enough actually to do a meaningful homework problem. Then, if you do the homeworks, the final exam will be based on the homeworks. So if you do the homeworks, you should do okay in the final exam. So that's one way the homeworks are important. Also, there'll be a score, and at the end, I write down 2 numbers for each person, which is the sum of your homework scores and your final grade. And then I try and weight them in the sense that if you did all the homeworks and you didn't get a really do terrible on the final, like a 0, if it indicates you actually did the homeworks, then that'll be like a floor. That'll be like a C. And then after that, things depend primarily on the exam. So if you did very well, that's an A. If you did okay, that's an A minus, and so on down. So if you in fact do the homeworks, then, although I don't want to promise this, there's no contract, if you in fact did the homeworks, then you should be guaranteed a C in the course. Nobody who does the work should flunk the course at this stage of the game. Now, as far as the midterm goes, that'll count like a homework, which means it doesn't count very much. So it counts something, but it's primarily for your benefit, to give you feedback, and not for the final grade. Because my philosophy is that the grade at the end should reflect your knowledge at the end of the course, not your knowledge at the beginning or the middle of the course.
There will be 1 exam and 1 final, right?
Yeah, 1 midterm, 1 final, right.
And the midterm is going to be testing us primarily on just the theorems and how to apply them.
Just the stuff we've been doing in class. So the way to study for the midterm is try and understand what's happened in class, because the book is sort of a reference, but I wouldn't read the book too much. I wouldn't put too much stress on the book beyond the topics that were covered in class, because the examples that given in the book, to the extent that they're the same examples that I gave, that's a good reference to see it written down more in hard copy, and to see the author's argument.
Doing exercises from the book.
I wouldn't worry about the exercises from the book, except the ones that I discuss. I mean, if you want to do them, sure, that's great. If you can do them, fine. But I would put the emphasis on trying to understand what's done in class, because the exercises in the book, some of them are tricky or they're difficult for the wrong reason. Because you can make these problems arbitrarily hard without having any new concept in them. Okay on the exam? Okay, so we're talking about, so the exam is Thursday, October 9th. And I'll discuss a sample exam prior to that. So that'll be a sort of a dry run. So we're talking about independence, section 3.5. And the definition of independent is we say A and B are independent if. And the usual definition is this: the probability of A and B occurring jointly, that is a point that occurring that's in both A and B, is the product of the probability of A times the probability of B. And but an equivalent statement, which is actually intuitively more meaningful, is this. You could say the probability that A is independent of B is the probability that is A is independent of B if knowledge of B does not affect the probability of A. But similarly, if A is independent of B, it ought to make sense, it ought to be that B is independent of A. And that expression would be the probability of B given A is the probability of B. So typically what people do is they use these as motivation for the definition, or the theorem, however you want to look at it. And then it turns out that you can show that each of these implies the other two. You can use anything you want to check for independence. But typically the way I like to look at it is, think about it this way. But then if I want to check to see whether or not two events are independent, ordinarily what I do is I calculate this probability, I calculate that, and I calculate that, and I check to see whether or not the left-hand side equals the right-hand side. And if it does, they're independent, and if it doesn't, then they are not independent or dependent. And then there's lots of examples of this, and as usual, there's many cases in which it's obvious whether things are independent or not, and then there are other cases where it's not so clear. And in fact, whether or not events are independent is often one of the most important questions. For example, I think I gave this example. You could talk about cancer, for example. So here is a cancer. Let's let C mean cancer, or lung cancer. Let's be specific. And S means smoker. And you want to ask the question, is the probability of having lung cancer, given that you're a smoker, how does that relate to the probability of having lung cancer without regard to whether or not you're a smoker? And the data seems to show, and everybody seems to agree, that the probability of having lung cancer if you're a smoker is greater than if smoking is not part of the data, or surely if you were a non-smoker. So in that case, cancer and smoking would not be independent. And so the question there is to look at something like cancer and smoking, take some data, and try and determine from the data whether or not cancer and smoking are independent. Now, if they are dependent, then that only indicates a statistical connection. It doesn't mean that there's a physical connection or a cause. But most people would say, well, if this is true, then it must be that smoking causes cancer. But you could argue from a statistical point of view that it's just as reasonable to say that cancer causes smoking. All this says is that these are not independent. That is, knowledge of one affects the probability of the other, but it doesn't say that one causes the other. So in fact, you could say, which is what the Tobacco Institute scientists, I use scientists in quote there, the Tobacco Institute scientists used to make that argument when this data was first noticed, this non-independence between cancer and smoking. So how could you criticize that? And, or why, how could you explain that? And one answer is you could say, well, it might be that tendency toward lung cancer is genetically linked. In other words, some people have a genetic predisposition to get lung cancer. They're more likely to get it than other people. And it might also be that there's a genetic inclination for smoking. That's maybe harder to see, but smoking is an addiction, and people who start to smoke, some people are more sensitive to nicotine than others, are more likely to become addicted. So therefore, it's possible that you could argue that to some extent, smoking is a genetic characteristic, and to some extent, cancer is a genetic characteristic. And then it's possible that there might be some gene, which might be the same gene, which might make you more inclined to get cancer and more inclined to be addicted to nicotine. And so then these two things would be linked, but cancer wouldn't cause smoking, and smoking wouldn't cause cancer, but they would in effect both be caused by something else. So statistics does not tell you causality, it only tells you connection, correlation. Of course, when you see this kind of connection, then you think about it and you say, well, it seems to me most likely, most reasonable, that in fact it's the smoking that actually causes the cancer, because you're taking these chemicals into your lungs, and so then you investigate it in the laboratory, and you have some monkeys or dogs smoke or something of that sort, and then through laboratory analysis, through more biological scientific research, you determine that in fact smoking does cause cancer, and so this is not the proper connection. But the point I want to make is that the statistical analysis only shows a correlation. It doesn't show that one causes the other. But you can see this is very important, because every day you pick up the newspaper, there's some study that shows that something causes something else. I don't know. Taking baths in hot water causes green hair or something like that. And then you wonder, well, did the baths cause the green hair? Did the green hair cause the baths? I don't know. Or did it not make sense at all? Which is, half of these don't make sense at all. And one of the reasons they don't make sense at all, when they don't, is because the sample sizes are too small. In any event, this is what is meant by independence. And in our case, since we're not looking at it from a statistical point of view, remember, in statistics, what you do is you look at data and you try and understand what caused the observation. In probability, you make mathematical models and you try and predict what would happen if a certain experiment were performed. So they're like inverses of each other. So you do probability first, and then you do statistics. So we'll do statistics, we'll start it later on in the course. So statistics can be viewed as an application of probability. Okay, so let me give an example here. And let me go back to the dice problem. So here's the usual stuff. So suppose we have two dice. I'll call them X1 and X2. 1, 2, 3, 4, 5, 6. And this is X1. And 1, 2, 3, 4, 5, 6. So this would be X2. And then we have this sample space, which we defined earlier, in which in the sample space, the points in the sample space correspond to the values that can occur when you roll the two dice. So the coordinates of these points are the values of the dice. And what we said when we started was, we said we're going to make this is a model now. Very important to recognize that the model is the mathematical description, which may or may not be a good description. But whatever it is, once you have the model, then the manipulation is mathematics. So once you have the model, the manipulation is right or wrong, but the determination of the model originally, that's an art rather than a science. That's outside this range. So in our model, we said, well, we're going to look at these 36 points, and we will assume that the points are equally likely. In other words, the probability that x1 is equal to I and x2 is equal to j, we said was 1 over 36 for I and j equal to 1 through 6. Okay, now the reason for that was because it didn't seem any reason why any of these particular points should occur more or less often than any other one. So we made the simplest, least presumptive assumption, which is that they're all equally likely. So if they're equally likely and the probabilities must sum to 1 and there are 36 possible points in the sample space, then each must have probability 1 over 36. So then the question is, are the dice independent? So you can answer that by saying what I need to do is I need to check whether or not the probability that x1 is equal to I and x2 is equal to j, is that equal to, I'll put a question mark there, the probability that x1 is equal to I times the probability x2 is equal to j. That's how I would check for independence. Well, we already know what this one is 1 over 36. Okay, but what's the probability that x1 is equal to I? Well, first of all, what I've done here is I'm really asking whether the dice are independent because I want to check this for every value of I and j. But it's possible that this might be true for some values of I and j and not for other values. But in this case, because of the symmetry, as you'll see, if it works in one case, it works in every case. So for example, how am I going to get the probability that x1 is equal to 1? So to get the probability that x1 is equal to 1, what I would do is I would look at x1 and I'd say, how can x1 equal 1? That corresponds to this event right here. So this is the event x1 is equal to 1. So I could calculate that either by counting the number of points, which is 6, and dividing by 36, or I could say the probability is 1 over 36 plus 1 over 36 and so forth 6 times. I would still get 6 over 36. So in other words, the probability that x equals 1 is the sum of the probabilities of these points, and that's obviously equal to 6 over 36. And in fact, you can see it's the same for every one of these columns. So for every I, this probability is 6 over 36. And likewise, you can see that if I want to calculate the probability that x2 is equal to j, for example, if j is equal to 3, so this is x2 is equal to 3, then I would sum the row, and of course I'm going to get exactly the same thing, 6 over 36. Of course, 6 over 36 is 1/6, 6 over 36 is 1/6, when you multiply them out, you get 1 over 36, so the answer is yes, so the dice are independent. Now, these values is 6 over 36, which of course is 1/6, which is what everybody thought they knew from the beginning. Those values are called the marginal probabilities, because I have here the joint probabilities. That's what these are. These are the joint probabilities, because they tell you what x1 and x2 are jointly together. And then the marginal probabilities are obtained by adding up the values in the columns or the rows. And so if you write the answer in the margin, I think that's where the term came from, that means that those values are now called the marginal probabilities. Okay, so these values right here, well, adding them up, I'll just write it here. These are called the marginal probabilities, because you would get them by adding things up and writing the answer in the margin. Okay, so the answer is, in this case, that if I have 2 dice with 36 possible outcomes, and those outcomes are all equally likely, then the probability that any point occurs is the product of the probabilities for each row and column. In other words, the dice are independent. Because in this case, not only are the events independent, particular I and j, but in fact it's true for all I and j, so we would say that the dice are independent. That's not surprising. I mean, you would expect that if this model were to make were to produce anything else, then it probably wouldn't be right, because the dice ought to be independent because they're physically distinct. But we don't know that, or we might not know that. There might be magnets in them, or the dice might be biased, or who knows? Who knows what the reason is. Okay, so this thing implies that the dice are independent. Now what about the other way around? If I assumed that I knew only these probabilities here, that is, if I assumed that I had 2 dice, and die number 1 had probability 1/6 for each of its 6 faces, and die number 2 had probability 1/6 for each of its faces, and then I said, okay, now, what's the joint probability? I would say, well, if they're independent, then The joint probability would be the product of those two individual probabilities. And of course, I get the same thing back again. So in this particular example, everything hangs together. Because what it says is that if the points in my sample space are all equally likely, then the dice are independent. And if the dice are independent, then the points in the sample space are all equally likely. And of course, if the points in the sample space are all equally likely and the dice are independent, what that means is that each die is equally likely to get each of its faces. And so your common sense argument shows that everything works. But it works because we made the right assumption. For example, I could have said at the beginning, I could have said, okay, I've got these 36 points in the sample space, and now I have to assign probabilities to them. So I assigned the probabilities as being all equal because there was no reason not to. There was no reason to prefer that and assume that one point would happen more often than another. But suppose that weren't true. Suppose I actually took two dice and rolled them a zillion times and observed the data, took the frequencies, and I got numbers that, of course, have to add up to 1, the total, but they don't all have to be equal. So, for example, this one could be a little bit less than a 36, and this one could be a little bit more, and so on. As long as I had the property that the sum of all 36 of them added up to 1, then I would have a legitimate assignment of the probabilities. But if I took those numbers and then made the same check, maybe it would work and maybe it wouldn't work. If it works, then the dice are independent. And if it doesn't work, then the dice are dependent. So with a dice problem, it's sort of obvious because you wouldn't assign your sample space any other way than this unless you had evidence to the contrary. But evidence to the contrary, if you had such, would probably mean that the dice are not independent, which means that there's something that's linking them together, whether it's an invisible string or a magnet or something like that, or somebody cheating, who knows. Okay, so that's an example. But let's look at another example related to the same thing. Suppose I ask this question. I'll do it here. Suppose they said, what's the probability that x1 plus x2 equals 8, given x1 equals 5? I think those are the numbers I want. Actually, I'd done it the other way around. Let me do it the other way around. Although it would work both ways. What's the probability that x1 is equal to 5, given x1 plus x2 is equal to 8? Okay, so now we have to calculate this probability. And if I work directly from the definition of conditional probability, I see that, well, I've done this before. Actually, the easiest way to do this is the reduced sample space argument. So let's look at x1 plus x2 is equal to 8, and that would correspond to these points right here. Let's see, this is, no, these points. I misdrew it. Okay, so this is x1 plus x2 equals 8. In other words, these are all the points such that the sum of the row numbers and the column numbers add up to 8. So this is 2, 6, 3, 5, and so forth. So there are 1, 2, 3, 4, 5 such points. So that probability then would be, there are 5 points in the reduced sample space, and I want the probability that x1 is equal to 5. That would correspond to this point right here. So the answer would be 1/5. Okay, so if the answer is 1/5, we know by direct calculation that that is not equal to 1/6, which is the probability that x1 is equal to 5. So therefore, the events x1 equals 5 and x1 plus x2 equals 8 are not independent. Okay? The fact that they're not independent means that knowledge of one affects the probability of the other. So here, by telling you that the sum of the dice is 8, that changes the probability that a particular one of them is 5, from 1/6 to 1/5. So this provides information about that, so therefore they are not independent. But this can be a little bit tricky, because suppose I ask this question. Suppose I said, what's the probability that x1 is equal to 5 given x1 plus x2 equals 7? So at first glance, you'd say, well, if those two things are independent, those two things are independent. But they're not, because all I have to do is count. If I look at x1 plus x2 equals 7, that corresponds to this reduced sample space right here. And there are 6 such points, so the probability that x1 is equal to 5 is one of them. So let's see, this is 7 right here. x1 is equal to 5 is this one. So the answer is 1 over 6, which does equal the probability that x1 is equal to 5. So in other words, the events x1 is equal to 5 and x1 plus x2 equals 7 are independent. So what this says is that if I tell you the sum is 7, I really don't tell you anything about the components that made up the sum. But here, if I tell you the sum is 8, then I do tell you something about the components that made up the sum. Of course, when you look at the diagram, it's easy to see, because when I tell you the sum is 7, I'm not eliminating any possibilities for either x1 or x2. But when I tell you the sum is 8, that means that x1 or x2 can't be 1. So since that information eliminates one of the possibilities, it changes the probabilities. Look confused. Okay, in this case, if I tell you that the sum is equal to 8, what I'm doing is I'm telling you that I'm looking at only a sample space that has 5 points in it. And one of those points is x1 is equal to 5, so the probability of that is 1 out of 5, which is not the same as the probability that x1 is equal to 5, which you already know is 1 out of 6. So that means that these events, this and this, are dependent. They are not independent. Now, why is that? One answer is that as soon as I tell you that the sum is equal to 8, then I know that 2 possible points have been eliminated, because I can't have x1 is equal to 1, because if I did, the sum couldn't be 8, and I can't have x2 is equal to 1, because if I did, the sum couldn't be 8. So this information eliminates some possibilities for x1. x1 can't be 1. So if I know x1 can't be 1, then the probability that it's 5 should be 1 out of 5 remaining possibilities, not the original 1 out of 6. So this fact tells you some information about this, the likelihood of this, because it eliminates one of the possibilities that x1 could be. On the other hand, if I'm looking at the event x1 plus x2 is equal to 7, then I'm looking at this subset instead of the diagonal above it. Now that subset has all 6 possible points for each of the individual dice. So if I know that the sum is 7, that doesn't eliminate any possibility for what x1 and x2 could be. So in that case, it turns out that since I don't eliminate any possibility, that means that, in effect, I'm not giving you any new information. And therefore, the probability that x1 is equal to 5 is just the same as if I didn't know that the sum is 7. So if you understand this, you can see intuitively why these things are the way they are. But you have to be careful about it, because you can see that in more complicated situations, you might argue by analogy, and in this case, you would get the wrong answer. Let me do another example. Let me do one other thing before I do this next example. What about if the events, I'll do it over here. Suppose that the intersection of A and B is empty. Are A and B dependent or independent? Independent. Everybody say they're independent? Okay, it's exactly the opposite, of course. A and B are dependent. This is a common mistake. I'm not sure why, but what does this say? I've got these two sets in my sample space, A and B. Okay, now, if they're empty, that means there's no overlap. So therefore, if I tell you that A occurs, then B can't possibly occur. So therefore, knowledge of A gives me information about B, so they are dependent. So, independent is not the same thing as disjoint. In fact, if the events are disjoint, they are necessarily dependent, and in fact in a very strong way. Because if I know that the events are disjoint, that says that they can't both occur. So if one of them occurs, the other one must not occur. Now this comes right out of the formula as well, because according to the formula here, let's look at it right here. If I apply that formula here, then since AB is empty, the question is the probability of the empty set equal to the product of the probability of A and the probability of B? Well, the probability of the empty set, as we know, is 0. So unless A and B, or A or B, have 0 probabilities themselves, then these events are not independent. So usually, just to avoid these kind of problems, when people describe this stuff in an elementary course, they start off and they say, let's assume that the probabilities of A and B are not 0. Okay, so if the probabilities of A and B are not 0, then if they do not intersect, then they are dependent events. On the other hand, if they do intersect, it doesn't mean they're independent. You have to check and see, as we've just seen. So, again, we have some mathematics which makes things mechanical for you, but there's intuitive meaning behind it. Very important, because if events are independent, that means that knowledge of one does not affect the probability of another, and if they're dependent, then knowledge of one does affect the probability of the other. And if you want to see whether or not things are linked in a statistical sense, whether there's some kind of physical causality or not, then what you want to do is you want to check and see whether or not things are dependent or independent. So this is an important point. Okay, let's go back to that earn example that we did a long time ago. Okay, so we looked at the earn, and remember we had R reds and W whites. And there were two ways to sample. We could sample with replacement, and we could sample B without replacement. And the question we wanted to ask was, what's the probability of red, let's see what we calculated. We calculated the probability of red on the second trial, sampling with replacement, and the probability of red on the second trial, sampling without replacement. And we found out that they were equal. We calculated each of those separately, and we found out, surprisingly, that the answer was R over R plus W. And in fact, what we showed was that the probability of red on any trial, whether you're sampling with or without replacement, was equal to the ratio of R over R plus W. So remember, we did that. Everybody voted the wrong way, but we proved it. And we gave other arguments for it so that everybody should have been convinced. But the reason that people got mixed up on this was because people were assuming that if I'm sampling with replacement, then the trials are independent, which they in fact are. And if I'm sampling without replacement, then the trials are not independent, which is also true. But the assumption that people were making in their heads was that if the trials are independent, then the probabilities would be the same each time. And if the probabilities are dependent, then the probabilities would be different. And that's why people were surprised at this. Okay, so of course, at that time we hadn't defined dependence or independence, but that was what in everybody's mind. Because when you calculate probabilities without replacement, you have to take into account that as the trials progress, the composition of the urn changes. And on each trial, the probability of getting a red or a white depends on the composition of the urn. The thing that made it work out this way was that you didn't know what the composition of the urn was, so therefore the changes in either direction canceled each other out, and so you got the same answer after doing some algebra. So that was relatively surprising. Okay, so let's check for independence. So what's the probability of, under A, sampling with replacement of red on the first trial and red on the second trial? Okay, so working directly, what I'd say is this. Okay, I'm sampling with replacement. So that means that the sample space could consist of the number of possible values that I can have on the first trial, the number of possible values I can have on the second trial, and I would multiply those together. So that means that the total number of points in the sample space would be R plus W squared. Because there are R plus W possibilities for the first ball, and there are R plus W possibilities for the second ball, so there are R plus W squared ways I can write the identities of the colors of the first ball and the second ball as I pull them out. Okay. So if I assume that every every point is equally likely, then this is the total number of points in the sample space, and I would divide that into the number of points in the sample space that correspond to red, red. But how many ways can I have red, red? Well, there are R possibilities for the first one, and there are R possibilities for the second one, so there are R squared, total number of points in the sample space that correspond to red, red, and there are R plus W squared points in the sample space that correspond to something for the first two trials. Okay, now, what's the probability under A of red on the first times the probability under A of red on the second? Well, we already worked that out. We know that the probability of red on the first is R over R plus W. And we proved that the probability of red on the second, if I got red on the first, doesn't make any difference. The probability of red on the second is also R over R plus W if I'm sampling with replacement. So obviously, these two things are equal. So the trials are independent. Trials are independent. In other words, in each trial, what happens is independent of what happened on the previous trials if I'm sampling with replacement. Of course, everybody knew that. That's how you got that's why there was confusion about this in the first place. Okay, suppose I'm sampling without replacement. So now I want to calculate the same things, but I want to put a B under here. Okay, what's the probability that if I'm sampling without replacement, that I will get R on the first and R on the second? Well, now we can make a more direct argument. In fact, I did this. I'd say, well, here's the way we could do it. We could say that I'm going to pull out two balls at one time, and if they're both red, then obviously I must have had red on the first and red on the second. So, to look at that, I'll say, well, let's see, how many ways can I do that? There are R plus W balls in the urn, and I can pull out two of them. That's the number of subsets of size 2. Remember, I'm pulling them out together, and then I'm going to put them in order. Okay, so this is the number of subsets of size 2 I can get. Now, how many subsets of size 2 can I get such that they're both red? Because the only way that they can have red on the first and red on the second is that both balls that I pull out must be red. Well, from the red balls, I must pull out 2, and from the white balls, I must pull out 0. Okay, but we also know that the probability of red on the first and red on the second. Okay, so let's see, I'll write that, didn't give myself enough space. Let me go up to here. Okay, from this we know that the probability of red on the first sampling under B is, of course, R over R plus W. But we also know, because that's what we showed here, that the probability of red on the second, if I'm sampling without replacement, is R over R plus W. So therefore, since that which is the same as this is not equal to that, in other words, therefore, the probability under B of red 1, red 2 does not equal the probability under B of red 1 times the probability under B of red 2. So they are not, trials are not independent. Now maybe I'm killing a dead horse here because we already knew that. That's what was misleading to everybody in the first place, even though we hadn't defined independence at that time. But here's the point. The point is that I can see, because we calculated it now, that if I pull the balls out of the urn one at a time and I sample with replacement, then the trials are independent, and then the probability of having red on every trial is the same. If I pull out the balls and I sample without replacement, then the trials are dependent, as I just proved. They're dependent because on each trial, what happens depends on what happened on the previous trial. But if I ask the question, what's the probability that on any particular trial I get a red, it's exactly the same for a single position, whether I sample with replacement or without replacement. So these two things are the same under A and B, but this thing right over here is different under B, because here it is, as opposed to A. Here it is. So this is another thing you got to digest. In other words, the reason that most of you had a problem with this originally was in your mind, you're thinking that the trials are dependent, which they are. We just proved that. But that does not mean that the probabilities must be different at each trial. Because what we proved was that the probability is the same in each trial. If the only question I ask is, what's the probability that I get a red ball? This is what we proved. What's the probability that I get a red ball on the jth trial? And we showed that it didn't matter, if that's the question, it didn't matter whether I was sampling with replacement or without replacement. But if I'm sampling with replacement, the trials are independent, and if I'm sampling without replacement, the trials are dependent. Now, there are lots of examples in the book, and as I say, if I were you, I would just try and understand exactly what's here. Because what I'm going to give on the midterm is going to be some variation of something that's been done in class. So the typical midterm is that there are some questions that are basically the same as what's in class, except that the names are changed to protect the innocent. And then there's always some question that's slightly different from what was in class. Those are the harder problems. But if you just, in a scattershot way, try and look at the examples in the book, it's probably misleading because you'd have to read it. It's like the people always ask me for homework 0, what should I review in calculus? Should I get a calculus book and review it? My answer is no. Calculus book is that thick and you only want a little piece here. So this is the same idea. Don't stay focused on it. Okay, so any questions about that? So if not, then I want to go to page 115. And notice on the way that, let's see, two things I wanted to say if I'm turning these pages. On page 109, it says, important remark. That's this thing right here. That's a reference for that. On page 111, there's the example 3.27 called the jailer's paradox, and that's actually the Monty Hall problem again. I think I mentioned that when I did the Monty Hall problem. And in fact, on page 112, he talks about Parade Magazine and Marilyn Vos Savant and all that kind of stuff. And now I want to go to page 115. Okay so far? I always get worried when people don't ask questions. It means everything is transparently obvious, or you have no idea what I'm talking about. So we could vote on that. You probably all vote for no idea what I'm talking about, but since you always vote wrong, it's transparently obvious.
Why does the jailer's one come up with a different answer than you did?
Come up with a different answer?
Yeah.
How does he come up with a different answer?
This one in here and this one in here shows that there's no information is provided.
Because the question is slightly different.
Okay.
You got to read it, but it's the same problem.
I mean, it's the same problem, but apparently it's worded slightly different.
Right.
It's a different answer.
Right. Actually, the wording it slightly different, taking a different point of view, is critical in making the problem famous. Because the reason that Marilyn got all this attention was because she could write it in a way that looked like it was just common sense. And the idea of putting it in the context of a quiz show that everybody watches with goats and cars. So that's what brought it to the attention of the public at large. And then all these people who had considered what was essentially the same problem, but with slightly different viewpoint and different names, got annoyed because here's Marilyn writing stuff in Parade Magazine and claiming she's the smartest person in the whole damn world, and that just pisses people off. Especially when they couldn't get the right answer.
Especially when her answer is different than
Right, it's different from what common sense and also from what most even probability and statistics people thought. Although I think that largely their problem was that they didn't take it seriously. They read it in Parade Magazine. They didn't even want to admit that they were reading Parade Magazine. They probably had to say that their kid was reading Parade Magazine and said, "Hey, Daddy, here's a probability problem." Okay, so I want to go to example 3.30. Interesting example. This is page 115. And the question is this. It says we draw cards one at a time at random and successively from an ordinary deck of 52 cards with replacement. What is the probability that an ace appears before a face? Okay, so what you're doing here is you shuffle the deck, you reach in, you pull out a card, and if it's an ace, then the ace occurs first. If it's a face card, face meaning Jack, Queen, King, or Ace. There are 4 face cards. If it's a face, then the face occurs first. And that is right. That is what a face card is, right? Jack, Queen, King, Ace is a face card. No?
No.
Jack, Queen, King. Yeah, I guess not.
Jack, Queen, and King have faces on.
No, I think Ace is a face
He's
card.
asking ace appears before a face card.
Right. So they're defining a face card.
Right. Okay.
Yeah.
Okay, so an ace is different from a face, right? So face is Jack, Queen, King. All right. So I'm going to reach into the deck and pull out the card and see whether I got an ace before I get a face. And if I got neither ace nor face, then I put the card back and I do it again. So that means that obviously the trials are independent because I'm sampling with replacement. So the question then is, what is the probability that if I do this as many times as necessary until I either get an ace or a face, the ace will occur first? So the difficulty there is that the number of trials is potentially infinite because you could simply keep drawing cards forever and never get an ace or a face.
You're saying you replace it at an arbitrary place in the deck?
Well, you could replace it in an arbitrary place in the deck, but you have to shuffle them. Because if you, that's right, because if you placed it in an arbitrary place in the deck and then took the first card that was in the deck, you wouldn't take the one you would just put in there. So by sampling with replacement, that means it's possible to draw out the same card twice in a row.
What is a face card?
Okay, face card, that means if you have a deck of cards, the jacks, queens, and kings have pictures on them. Instead of being called 11, 12, and 13, they're called jack, queen, and king. And so those are face cards. So we have aces, faces, and then the others are numbers. Okay, so I want to ask the question more generally, because this is a general kind of question. I'm sampling with replacement. That is, I got this infinite population, say, and I'm going to reach in and I'm going to ask for the probability that some event occurs before some other event. And so in this case, there are actually a partition of the sample space into three possible events, which I'll call A, B, and C. So here's my sample space, and here is A, B, and C. So it's a partition. So that means that every time I conduct the experiment, I get either A or B or C. So in the context of this particular problem, A would be face, B would be, or A could be ace, B could be face, and C is anything else. So I don't have to, the point I'm making is that there are three things. Something happens, something else happens, or anything else happens. And they are mutually exclusive and exhaustive. And I'm going to conduct this experiment, and I want to find the probability that in this set that A occurs before B. So let's call it little p. And I have the probability of A before B. And I'm going to sample with replacement until A or B. If C occurs, I just repeat the experiment. Okay, so I'm sampling with replacement. I have independent trials. So this is a common setup now. You can imagine there's lots of problems out there where you're going to conduct an experiment over and over again until either this occurs or that occurs, and you want to know the probability that one specific one occurs first. So that's the probability. Let's call that P. So what's the probability that if I do this until I get either A or B, that the A will occur first? Well, one possibility is I can get A on the first trial. So if on a single trial I get A, then obviously A occurred first. But I could also get C and then A. Remember that these events are mutually exclusive. So the intersection of A with C, what this means then is that this is the probability that I get C and I get A. So these events are mutually exclusive, because if I get A first, then I can't get C first. So this is the probability of A, that's the probability of C, and then A. But then there's the probability of C, C, A. And then there's the probability of C, 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 A, and so forth. So I have this infinite series. So I have a string of C's and then A. If I have a B any place, of course, then a B would have occurred first, and then I would not have had this event, A before B. Okay, so now the next step is, well, these are independent trials. Okay, so the fact that they are independent trials means that the joint probabilities factor into the product of the individual probabilities. So the probability of C and then A is the probability of C times the probability of A. And the probability of C, C, and A is the probability of C times the probability of C, which is the probability squared, times the probability of A. And the next term would be the probability of C cubed, probability of A, and so forth. So this equal sign follows because I have independent trials. That's what allows me to take this probability of a string and break it into the product of the probabilities of each individual trial. Okay, now the next is some arithmetic here, because what I'm going to do is I'm going to factor out the probability of A, and then what I have left is 1 plus the probability of C plus the probability squared of C plus the probability cubed of C, and so on. And everybody recognizes this thing right here. Well, let's see, I'll just write it like this. I have the probability of A. And then the thing in brackets everybody recognizes as a geometric series. In other words, what everybody knows from high school is that 1 plus x squared and so forth is equal to 1 over 1 minus x as long as the absolute value of x is less than 1. That's called that's the geometric series. And of course, in our case, what plays the role of x is the probability of c. Since the probability of c is a number between 0 and 1, then obviously its absolute value is less than 1. We're assuming here that the probability of c is less than 1. Okay, so I factor out the probability of A, and then what I'm left with is 1 over 1 minus, and the minus is the probability of C. But, never leave myself enough room, so I need one more step here. So let me bring that up to here. I can get rid of this thing here, I think. Actually, what I just erased is exactly what I need, because remember that our sample space had a partition A, B, and C. So you can see that since these probabilities must sum to 1, then 1 minus the probability of C is the probability of A or B. So this becomes the probability of A, that's that guy right there, times 1 over, so the denominator is 1 minus the probability of C, which is the probability of A plus the probability of B. So this is our answer right here. Okay?
One more time, where the denominator.
Okay, so let's go through this again. I'm going to perform this sequence of trials, and they're independent. And I want to ask for the probability that A occurs before B, and there are 3 things that can happen, A, B, or C, and they're mutually exclusive. So I say the probability that the A occurs first is the probability of A on the first trial, plus the probability of C and then an A, or CC and then an A, and so forth. And since the events are independent, that means that the probabilities of the strings factor into the product of the individual probabilities. So that's what I wrote here. Then I recognize that I can factor out the first term, and what's left is a geometric series, and the value of that sum is 1 over 1 minus the thing that's being raised to a power, so that's 1 over 1 minus the probability of C. And then I see that since the probability of A plus the probability of B plus the probability of C must add up to 1, 1 minus the probability of C is the probability of A plus the probability of B. Okay? In other words, from here, let me erase where it says geometric series. From here, we know that the probability of A plus the probability of B plus the probability of C equals 1. So 1 minus the probability of C is the probability of A plus the probability of B. I put that back into this expression, and I see that that's my answer. So that works in general. So for the particular case at hand, let's go back now to the example 330 where we're talking about the card problem. The answer would be equal then to the ratio of these probabilities. So A is the probability of pulling out an ace, and so that would be, let me write that down. Okay, so I'm going to get rid of this thing here. And I'll say, let A indicate ace, and B indicate face. And so the probability of ace before face A before B, or I'll write it A before F, probability of ace before face, is equal to the probability of an ace divided by the probability of an ace plus the probability of a face. Now, what's the probability of ace? Well, there are 4 aces in the deck, so the probability of an ace is 4 over 52. Denominator, there are 4 aces in the deck, so the probability of an ace is 4 over 52. There are 12 faces, because there are 4 jacks, 4 queens, 4 kings. So that probability is 12 over 52. The 52's cancel, and I'm left with 4 over 16, or 1/4. Okay, so that's the answer. That's the example that he does in the book.
Yeah, but I mean, I got a question. It means like 25%. Like, I mean, you have an ace before face. If you shuffle the card and like take it, it's a 25% chance that you'll get an ace before a face.
Yeah, that's what it says, right. 4 chances out of 16, 1/4. I'm not sure why that's surprising. You know, it has to be something, but why? I don't know why you're surprised.
I think it would be like very small, I thought.
No, I mean, the chance of getting an ace on any trial is 4 out of 52. The chance of getting a face on any trial is 12 over 52. And every time I get something else, I ignore it. So, I don't know. Well, anyhow, that's what it comes out to be, and it's a direct application of this. Okay, and so the author uses this example, but to me it's a little bit misleading the way he does it, because it makes it look like it's special to this problem and not an example of something that's a general model. Yeah.
If you did it with a reduced sample space, just the aces and the face cards, would you come up with the same answer? Because the other cards are inconsequential, really.
Well, that's a good point. In fact, that's exactly the point. So let me ask you another question. Suppose that you did ask the same question, but you sampled without replacement. Okay, this looks like it's much harder at first glance. Because if I'm sampling without replacement, then I can't go from this step to this step, because these are not independent trials. Okay? So suppose we sample without replacement. Same question. Okay, if I sample without replacement, then let me adapt your argument. Now I'm going to say, okay, what do I have here? I got this deck of 52 cards, and the deck has 4 aces, and it has 12 faces, and that's 16 cards, so whatever's left, those are the cards I don't worry about. So now I'm going to shuffle the deck once, and then I'm going to pick the cards out one at a time without replacement. Okay, so someplace in the deck there's the first ace, and someplace in the deck there's the first face. And I want to know the probability that the ace comes before the face. Now what happens is that as I deal out the cards, if the card that I'm dealing out is not an ace or a face, then I throw it away, I ignore it. So why not simply take the cards that are not aces and not faces out immediately? Because when I shuffle them and then start dealing them out, if I get an ace or if I get a non-ace or a non-face, I simply throw the card away and take the next card from the deck. So since I'm going to throw the cards away and take the next card from the deck, why not take them out of the deck immediately? So if I take them out of the deck immediately, now I have only 16 cards in the deck. Those are 4 aces and 12 faces. Okay, so now I have 16 cards. And of course, if those 16 cards are only aces or faces, that means that the first card I pull out is either an ace or a face, which means that the experiment is going to end on the first trial. So if I pull out an ace first, then if an ace is the first card I pull out, then I got the ace first. If the face is the card I pull out, then I got the face first. All the other cards are irrelevant, so I threw them away. So therefore, what's the probability of ace before face? Ace before face, sampling without replacement. And you can see that since I've thrown out all the cards that are not aces or faces, since there are 4 aces, and there are 4 plus 12 cards in the deck, 4 aces and 12 faces, the probability is 4/16, which is exactly what you got before. So now the question is this a coincidence or not? Is this just because this is a deck of cards, or does it matter whether I sample with or without replacement to answer this question? Anybody have an idea?
I think it matters.
Looks like it doesn't matter. But how can I get this? How can I get this argument? How can I prove this? Because the way I proved it in general when I was sampling with replacement is by using the independence. That was critical right here. Independence.
Well,
Yeah.
we changed this problem into an independent trial because it happened the first time.
Well, I changed it because what I said is that there's a fundamental difference between sampling with and without replacement. If I sample without replacement, then I know that the game has to end after a finite number of trials. Obviously, I can't sample more than 52 times. If I'm sampling with replacement, the game could go for hundreds of trials. And I also know that if I sample without replacement, then at each trial, the probability of anything is dependent on the previous trial. So it depends on what I remove from the deck. Of course, the argument we made before was that what you remove from the deck affects the probabilities, but since there are different things that can be removed from the deck, in effect, those different things all cancel out. Okay. What I want to ask here is, this argument is very special, this idea of being able to remove the cards that don't count, and then say, okay, now all I have left is these particular cards. There's a particular card that are either aces or faces. So I want to go back here and I want to look at this statement. What we proved was that the probability of A before B was equal to the probability of A divided by the probability of A plus the probability of B. And that was with sampling with replacement, where the trials are independent. But then I gave an example where I was sampling without replacement, and I got essentially the same answer. So is that true in general? So I want to look at this, and I want to ask this question. Suppose I say, what's the probability that when I play this game, I get an A, given that I know that the final result is only A or B? In other words, it's a conditional probability, because in both cases, what I'm doing is, if I get C, if I get something that isn't an A or a B, or an ace or a face in this case, what I do is I discard it, I ignore it. So if I ignore it, then I could change the question and say, well look, what's the probability that knowing that when I stop the game, it's either going to be A or B, in fact it's A. And now I'll just write down the definite conditional probability. So that would be the probability in the denominator of the event on which I'm conditioning, A or B. In the numerator, the probability of the intersection of the events, which is the intersection of A with A or B. But now these events are mutually exclusive. There's no overlap. So the probability of the intersection of A with A or B is A. The probability of the union is the sum of the probabilities. Well, it's the same answer. But in this answer, when I did it over here, I had to assume that I had independent trials. But over here, I didn't make any assumption about whether the trials are independent or not. I just used the observation that since I ignore the trials, I can do this reduced sample space argument and not have them in there at all. So this argument shows that this is true whether the trials are dependent or independent. It doesn't matter. And this whole argument here is just unnecessary. In fact, the author has this in the book. So he has a statement on page 117. And he says, this is on page 117. So, and here's what he says. He says it is interesting to observe that in this problem, if cards are drawn without replacement, even though the trials are no longer independent, the answer would still be the same. And then if you go and look at it, he has what looks to me like a complicated argument, which turns out, of course, to give the same answer. But the implication is that it works for this problem. And this insight, which says, well, why don't we just use this reduced sample space argument and recognize that we're ignoring the all the trials that don't result in A or B, and we're calculating a conditional probability. None of that makes any difference. And so you can write down the answer immediately by inspection. So in other words, the author's kind of misleading. He's implying that this is some coincidence for this particular case. But it's always true. All right, so the purpose of all of this, again, my purpose is to try and show some insight and to help you understand better what conditional probability means. Because once you realize that A before B simply means that you are going to perform the experiment given the condition that the answer must be either A or B. Once you recognize it as a conditional probability, then in one step you get the answer. And it shows clearly it doesn't matter whether you're sampling with or without replacement. Okay, so now I want to do one more problem. I'll do this next time, and this will end the chapter. And this puts everything together. This is the game of craps. So just let me say what craps is. Okay, so I have to be careful to put that S on there. Okay, the game of craps is the following. The player rolls 2 dice. If he rolls 2, and I'll write this down later. If he rolls 2, 3, or 12, then he loses. If he rolls 7 or 11, he wins. If he rolls anything else, that else is called his point. And then he rolls the dice continually until either he gets, say, 7 or he gets his point. If he gets the point first, then he wins. If he gets the 7 first, then he loses. If he gets anything else, he continues to roll the dice. So in other words, it fits in this context of A before B. But it's a little bit more complicated. But we'll work it out, and you'll see that everything in the chapter then is all contained in that one problem. And then that'll be the end of that chapter. Okay, so see you next time.